Log on, tune in, find out. Another good idea from Cambridge.
I want to thank the organizers of this semester for the invitation. I really have enjoyed already the first week and looking forward to another week here. This is joint work with Svetlana Dubinkina, who is my PhD student who finished this spring. Part of this, some of you I know have heard before, but hopefully it'll be a little bit, better or explained perhaps a bit more clearly. There's an idea in a paper by Lorenz in 1975. He proposed two different points of view on prediction. Prediction of the first kind, which is what we normally think of as prediction, and it applies to the weather. And it's the idea of the initial value problem, where we know the state of the system at some time t0, we know the governing equations, and we want to know the solution or the state of the system at some later time t. And this is normally limited by numerical accuracy and divergence of solutions due to deterministic chaos. And so there's some sort of horizon on what kind of time one can have prediction. And then the prediction of the second kind, which is more appropriate to climate, defined as a situation where the system indeed has fully developed chaos and is in essence sampling in its statistical equilibrium state, and then that equilibrium state is changing as a function of parameters which are changing on a much slower time. And so so from a numerical point of view, in the first case we need numerical accuracy, we need high accuracy, and in the second case we need that the system responds or gives the proper response to changes in its in parameters, and that it samples in a proper statistical equilibrium. And so that's actually the focus of this talk, is to talk about the statistical equilibrium states of numerical discretisations and how they depend on the discretization. So I'm going to work with the quasi-geostrophic potential vorticity equation model, just as a simple model. This is familiar to most people. We have Q is the potential vorticity, which is just advected materially in a divergence-free velocity field, and we have the stream function is defined. It's advected over a given topography H. So this is written symmetrically in terms of this Jacobian J, and we'll also always consider this on a 2 pi periodic domain. And then two conserved quantities of this system which receive a lot of attention are the total kinetic energy and the entropy, which is the second moment of potential vorticity. And then finally, in all the numerical experiments I do, I take a particular choice of topography, shown here, which depends only on x, and we do them at energy equal to 7 and kinetic energy equal to 7 and entropy equal 20, and this choice is motivated by a paper by Abramov and Maida in 2002, which we want to compare with. Now, just to illustrate that the equilibrium statistics of distinct discretisations can be really different. We have here the Arakawa schemes, which were developed in 1966, and they're based on 3 equivalent formulations of this Jacobi operator. So you can write this in 3 different ways, assuming Q and C are both twice differentiable. and then we can construct discretisations just by using, say, central difference operator on in x and y. We construct matrices dx and dy, which are central difference operators, and then we can, this is the pointwise Hadamard product, and so this is this directly looking at this form, we get this discretization, and based on this form we get another discretization, and based on this form we get another discretization, and because the operators don't commute, these are distinct discretizations. And the first one is the solutions grow unbounded. In the case of the second one, there's a discrete energy conservation, energy which is conserved, a discrete approximation of the energy. And in the case of the last one, there's a discrete approximation to the entropy, which is conserved. And then Arakawa showed that the average of these three discretizations conserves both energy and entropy. So we have three useful discretizations here. And now what we want to look at is the long time average of the stream function. So we just take capital N time steps with the method, and we average, and we get some average stream function, and that's shown here. So this is for the case of the method that conserves both energy and entropy. This is for the method that conserves energy, and this conserves entropy. And so these fields are climatic mean, are prevailing winds. And so you see that for the energy entropy discretization, we have rather strong shear flow. For the method that conserves only energy, we have no prevailing winds, and for the entropy conserving method, we have a weaker shear flow. And well, leave it there for now. Come back in a minute.
Any of them could be right.
Yeah, sorry?
Any of them could be right, of course.
Well, any of them could be right. Yeah, this is the question, exactly. Which one is right? So, to answer that question, we want to look at. We're going to do statistical mechanics for the Euler equations and for the methods, and the approach I'm going to use is information theory, which is it's not very physically based, but it's a little bit easier, and the results, the conclusions come out to be about the same. So the idea of information theory is that one wants to describe a probability distribution which has the least bias for a given set of observations. So the simplest example we can think of a probability space which has just n possible outcomes. So for example, rolling a dice, something like that, then n would be 6. And then we define the probability p, the probability p sub I to be the probability of event I occurring. And we want p sub I to be greater than or equal to 0, and we want it to sum to 1. Then we define the information entropy, which is given in this form, and we want to maximize entropy subject to the only constraint being that it is a probability distribution. Then, we can use the Lagrange multiplier method, maximizing this quantity. We take its gradient. A gradient of s is minus log p minus 1. A gradient of n is just 1, so we get the Lagrange multiplier here. We can solve for p, and we find it's a constant independent of I, and we can determine lambda based on the constraint, and we see that it's a uniform distribution. So the least biased distribution, given essentially no observations, is just a uniform distribution. Now if we move to a little bit more interesting situation, we can think of a finite dimensional phase space. So now this is the situation we have when we're working with discretizations. So we think of a discretization, and we have a d-dimensional discretization. So X is a discrete field in RD, and we want to find a probability distribution P, a probability density function on RD. We define the entropy as an integral over RD of it's analogous to the previous formula. And now we can say we have some observation, the energy. So we have an energy functional, and its ensemble mean over the phase space is given by the inner product with this P. We find that here we can denote it with E with braces, and then our constraints are again the normalization constraint, and that this mean energy has some observed value E0. Then we can again construct a minimization problem, this time with two Lagrange multipliers, lambda and b. We minimize that, we have to take variational derivatives. They look like this. And when we solve this for p, we get p is equal to a normalization constant times e to the minus beta e of x. So this is the Gibbs distribution from statistical mechanics. And this just follows from, this is then the least biased probability distribution under the observation of a mean energy E. Okay. And now if we take it one step further and we want to go to the continuum case, then we need our probability measure. So the idea then is that we represent the vorticity field as something which is at its finest scale uncertain. So it's going to be represented by a probability distribution P of x sigma, which gives for each point x in the domain a probability distribution over the possible values of potential vorticity there. So the P has to satisfy requirements that it's integral over at any point x, it's integral over all over the real line in sigma is 1, so it's a probability distribution at each point in the domain. It's also average over the domain is also 1, and then it should satisfy that the probability of the potential vorticity having a value between a and b is equal to the integral from a to b of p with respect to sigma. Okay. So given such a distribution, we can define a coarse grain or mean vorticity field by taking the integral of sigma with respect to p, and then a mean stream function, just using the usual definition, Poisson equation. And now we want to maximize this entropy with respect to the observation that the energy of this mean state is some given value, some observed value. So we're going to have to compute, again, variational derivatives of E with respect to P. So that's the variational derivative of E with respect to the mean Q, which is just C, minus C times the derivative of Q with respect to P, which is just sigma. And so we get a probability distribution which looks like this. So this is our equilibrium distribution, assuming that the only observable is energy. And you can go back and compute the mean state by integrating this, and you find that the mean state under an observation of constant energy is that the stream function has 0 is constant, and the vorticity is just h. And so this is actually what we see right here. So this is also what you get with the Arakawa scheme with constant energy.
Can you just remind me what the boundary conditions were?
Periodic,
Both ways.
both ways.
No linear conservation normal.
Right, circulation. You can add circulation in every slide of this talk, and it's
No linear conservation law that is not satisfied by some of those solutions. All those things are possible. I mean, non-linear conservation laws will be undermined by small scale being generated. What you're trying to address in this analysis, no linear conservation laws. I mean, some of those solutions aren't correct.
some of these solutions are not correct
So all those solutions are consistent with any linear conservation laws.
with any linear conservation.
Any linear conservation laws that apply.
Okay.
Well, I'm just asking the question.
Okay. Well, I'm not sure about that. I don't know. You're thinking of momentum or.
I'm just wondering if there's any sort of momentum conservation, or as well, I should ask about the boundary conditions. So there's any reason to suppose that something is actually that one of those solutions is inconsistent with a linear conservation property which would be preserved.
Well, I don't know, but I don't think that I think the Archival schemes conserve those. Yeah.
If you had a Gaussian, then that would be equivalent to an Ornstein-Uhlenbeck process. That would be the stationary distribution Ornstein-Uhlenbeck process, and so you'd have a conservation law of the fluctuation dissipation theorem of the second kind. That would mean that the fluctuations are being balanced by the deterministic feedbacks.
Mm-hmm.
And so basically you would have conservations, but it might not be what you think of as energy or momentum. On the other hand, if you have something that would be like fluctuating Navier-Stokes, then you do have to conserve momentum and energy microscopically. And that would also be consistent with this, I think.
Okay. But, I can't comment on it, but maybe we can discuss it later. Anyway, so one can go back and do the same procedure, but assuming an observation not only of constant energy but also of constant entropy, and this was then we get a classical result that was shown by Kreisman and Salmon and Carnival and Fredrickson, which is indeed that the distribution P is Gaussian in sigma at each x, and then we find that there's a linear relationship between the mean vorticity field and the mean stream function, and that's shown here in these plots. But these plots inset here are the loci of the mean stream function versus vorticity at each grid point. So we see the linear relationship in all cases, but in the case of energy conservation, it's vertical, and in the case of entropy conservation, it's more or less zero.
I'm just trying to understand this.
Yep.
So supposing so the equation says you rearrange PV with an incompressible flux. So supposing I said,
Mm-hmm.
well, since I don't know anything else, I'll assume it, and there's a cascade, I'll assume it'll all end up equal to its mean values and just get a uniform PV with the mean value of the original data. Which of those solutions would that give?
Well, it doesn't get a uniform PV in at any given time, right? It's the mean.
This is a climatic mean, so I was intending, if I didn't know any better, I'd say the end state ought to be just the average PV everywhere. Which of those solutions that was? Is that the middle one, or is that?
The average PV, so constant PV,
Yeah.
that corresponds to this one, I believe, right? No, this is PV is mean value 0, right? So this is PV is 0 everywhere. That's this case, right? Yeah. But that's, yeah, right. So
That's just a possible way of arguing if you don't know any statistical mechanics.
well, that's
no other information at all.
So this is one way to begin, and we use this a bit later. Okay, well, so of course the focus on the quadratic entropy is for the reason that it's numerically for sure the easiest non-trivial thing to preserve in terms of entropys. Also, it's automatically preserved by spectral methods, and so there was a lot of attention for that initially. But of course, it's only one of an infinite class of conserved quantities for the Euler equations. Any function of PV integrated over the domain is also conserved, and this can be seen to follow as a consequence of the material advection of PV and the fact that the flow is area preserving. So if we think about a piecewise uniform potential vorticity initial field, then we have patches of constant vorticity everywhere, and those patches, as they evolve, they maintain their area, and so this integral just becomes a sum over those patches of f evaluated at the level set value times the area of that patch, which is constant, and so in that way it's preserved. And this idea was used by Miller and coworkers and by Robert and coworkers to develop a more comprehensive equilibrium distribution, which includes a Lagrange multiplier, which ensures that each level set of potential vorticity maintains its area. So this was at the time considered the most comprehensive equilibrium description of the Euler equations. But there was a lot of discussion about to what extent this implies that all moments of vorticity are conserved and so forth, and there's a lot of question about whether this is a reasonable, with any bit of diffusion or any bit of viscosity, most of the larger moments are wiped out, and so this got a lot of controversy.
I think this is one of the mathematical difficulties about this is if you say the solution is a rearrangement of the PV and therefore conserves all the moments, but that set is not compact, so if you're trying to embed that in a compact set, you have to include all the weak limits, which includes the one where the PV is constant.
Yeah.
And so if you're trying to actually do a rigorous analysis that requires compactness, then you have to allow everything to just average out. You have to include those states, which are effectively infinitely fine-scale filamentation.
Right. This is also a matter of any kind of coarsening of the PV field. It depends on the scale at which you look at it in terms of these higher moments. So an alternative was proposed in 2002 by Ellis, Haven, and Turkington, and their approach was to actually only constrain the total energy and the total circulation, and to specify the fine-scale vorticity as a prior distribution, which could in principle be determined diagnostically. And this is, I think, the state of the art on this at the moment. Numerically, Abramov and Maida did some experiments in 2003 to try and determine if the higher moments of vorticity would have any effect on statistics, and so they used the Poisson discretization of Zeitlin, which conserves energy plus approximations of the first m moments of the vorticity field on an m by m grid to study the statistical relevance of the third moment of vorticity. And so what they did was they chose initial conditions with increased skewness, such that they could increase the third moment of vorticity. This is a scaled value to the ratio of the third to the second moment of vorticity. And as they increased that, they found that the linear relationship between mean stream function and mean vorticity became a nonlinear relationship, and in particular, the mean stream function field developed two-dimensional effects. They're not very visible there. Furthermore, their results suggested, because they didn't do anything, their initial conditions were chosen randomly, so the higher moments, the fourth, fifth, and up to mth moments, were just taken to be whatever they came out of the randomization, and they would also be conserved. And so the fact that for the third moment equal to 0, they obtained linear relationship led them to suggest that perhaps the higher moments higher than 4, were irrelevant for statistics. Okay, so what we wanted to do was we have this method that we developed with Sebastian Reich and Georg Gottwald and Colin Cotter and others. This is the Hamiltonian particle mesh method, and it was originally developed for shallow water equations, but one can apply it also to the QG equations by specifying, well, it becomes something like a point vortex method. So the idea is we have a set of k particles. Each particle has position xk, and it has a lumped potential vorticity capital Qk, which is just constant in time. And then these particles move around, and they have some kernel function with which they distribute their vorticity to a uniform grid. So this is a sort of coarse-grained vorticity field obtained this way, and then a stream function computed by solving a Poisson problem on the grid. And this is all made Hamiltonian by specifying just the kinetic energy approximation. We think of that as a function of the particle positions, and then we just we set up a Hamiltonian system which has the form of point vortices, and the particles move around in this motion, and you can show that we can construct a continuous stream function using the same basis functions. And if we do that, then we find that the particle motion is just given as the gradient, the skew gradient of this continuum stream function. And so the whole thing is the motion of the particles is that if we use a symplectic integrator, then the energy is conserved, the phase space volume is conserved, and also the velocity, the motion of the particles is also in a divergence-free velocity field. So this method then, well, one can argue that it also conserves arbitrary moments of the potential vorticity, and the argument goes of something like this. We have this continuum stream function field. We can take its skew gradient, and that gives us a continuum velocity field. And now we can think of, well, the motion of the particles is embedded in this. So for any motion of the particles, we have some sort of continuum velocity field, but in particular, these particles are embedded, their motion is embedded in that velocity field, and that velocity field is divergence-free. And so we can take with our initial conditions, and we can define the Voronoi cell associated with each particle, and we can think how that Voronoi cell deforms in this flow, and we can then evaluate an arbitrary function f just by taking its value at the particle times the area of this Voronoi cell after it's been advected in the flow, and then, well, this is constant. And so in this way, there's some idea of vorticity conservation. But it's some question whether this is a very meaningful conservation, because if we look at the moments of vorticity on the grid, so we compute the coarse-grained vorticity field on the grid, and we just compute moments of that field, and we see that the energy is exactly conserved, or on this scale, the circulation is exactly conserved on this scale. The entropy has a drift, which is, well, so this is a relative change. So I mean, it's clear it's near 100% drift in the entropy, and the third and fourth moments are just tremendous drift. So there's really doesn't appear to be any real conservation in these fields. So the question is this PV conservation with this method meaningful at all? And so well, we did some experiments to test that, but we also wanted to develop some sort of statistical model for the method. And the way we did that was we think of a piecewise constant initial PV field. It's not necessary to do that, but it makes the results make a little more sense. So we think of there being a number of PV level sets denoted sigma sub L, and for each level set there are K sub L particles with that value of PV, and then we let P I L denote the probability of finding a particle with PV sigma sub L in the neighborhood of grid point X sub I. So in other words, that its support overlaps that grid point. And then motivated by the fact that we have area conservation, we construct a prior distribution on PV, on this PIL, or on this, which is just delta A squared. It's the area associated with an individual particle. It's the area of its Voronoi cell, divided by the total area of the domain times the number of particles with that value of PV. And so the idea is, we think if we don't know anything else, we assume that every particle visits every grid cell equally often. Right? So this is our prior distribution. We introduce a relative entropy which incorporates the prior distribution, and then if we have no further assumptions and we maximize this entropy, then we find that PIL is just our prior, which says that at each, knowing nothing else, the probability of observing a given level set of PV at a given grid point I is just proportional to the area in the initial condition associated with that level set. So this is what we would, not knowing any better, might choose. And then if we add in the additional single observation of conserved energy, then we can derive an equilibrium distribution which looks exactly like the EHT theory. So now we did some experiments. We repeated the experiment of Maida and Abramov with, we chose our initial particle PVs from a given continuum prior, and then with a given chosen skewness or excess kurtosis. In the first case, up here we chose the same values as Maida and Abramov, and we do a pretty good job of reproducing their results here. And in the second case, we choose a non-zero kurtosis, fourth moment, and we choose zero skewness. And then for rather large values of this kurtosis, so relative kurtosis 10, 50, and 90, then we get some significant changes in the mean state there. So this shows that also the fourth moment can be relevant, but only when it's very, very large. Okay, so just to sum up, the idea is that for climates of prediction of the second kind, what's important is that your numerical method give the proper response, to respond accurately to changes in the definition of the statistical equilibrium, that the ingredients for statistical accuracy, I didn't really go into this, but all of the methods used are also conserve volume on phase space. So the Arakawa schemes, as well as the HPM method, they conserve phase space volume, which is necessary to have equilibrium statistical mechanics and some sort of conservation. And we saw that the distinct methods yield quite different statistics. And finally, we saw that for the HPM method, we have an analogous statistics to ETH. I guess I didn't say that, but the curves plotted here, the curves through the data points are the result of the theoretical predictions. And finally, we saw that for the HPM method, the PV seems to have the PV conservation really does seem to have some meaning besides just being a sort of mathematical construction. So, thank you.
Thank you.
Well, this was QG, so there was a fire deformation radius. So what was, so again, what I sort of expect to happen is you would be doing direct coarse grain prediction on scale larger than deformation radius, and you might think the statistical representation will be very suitable for the smaller scale. Is that the sort of thing you found?
So what you're suggesting is that you should have I think a rotation term, and is that?
Well, I mean, I think QG will have. I mean, so we'll have QG will have a finite deformation radius in it, which will be equal to something. I don't know what it was in your experiment.
I don't know either.
One is all non-dimensionalized.
So it was the domain size, was it?
The domain is is 2 pi. Yeah.
So it might be 1 over 2 pi times the domain size.
Yeah.
Okay, well, essentially because of the suppression of cascades in scale larger than deformation radius, it would be a reasonable strategy to say, well, the higher order moments matter more on the larger scales where things don't scramble. And it's the sort of representation that destroys the higher order moments. I was wondering if the sort of approach that really did try and satisfy the conservation laws for the coarse part of the solution, which on a scale larger than deformation radius, and a sort of statistical method where things are fundamentally is not clear, the higher order moments matter very much on scale smaller, and that was sort of philosophy you started with. You were going to say you were only going to use this young measure description for small scales, so that seemed to be a natural place to try and do your transition between the deterministic representation and statistical representation. I wonder if you found something like that.
Well, I haven't looked at other at other models. So
I thought your model should have had this in if it was QG.
I don't know.
Worth having a look.
Yeah, I would like to. Maybe you can.
It did seem to sort of fit the way you started the talk, where you were sort of going to mix, say, statistical representation and the explicit representation.
Mm-hmm. Yeah.
I'm just jet lagged enough to ask questions. I've always been kind of curious, if you have a coarse graining of a system, clearly we have all these limit theorems that say that you go to stochastic differential equations where, in the sense of economy and all this. So I've been wondering why you don't need to use a stochastic partial differential operator to integrate these equations.
You mean to get to observe to see ergodicity in the convergence
not
to
just
the.
to see ergodicity, but to have an accurate numerical result.
Yeah. Well, accurate in the sense of statistics, or.
Yes.
So, I think, of course, that's a good question, because the measures that I wrote down are all essentially canonical, more like Gibbs measures. So in other words, the probability of a given energy, or the probability of all. You have non-zero probability over the whole phase space, independent of energy, and yet the simulations are all done at constant energy and entropy in some cases. And what seems to be the case is that for these systems, as the dimension, or as the dimension of the discretization becomes large enough, you essentially have a called limit, where all measures, all probability measures become equal. And so even though we're really looking at what should really be a delta function or a microcanonical ensemble, it agrees with the canonical ensemble. And it seems to be due to the fact that if you look at the behavior of a single grid point, it's exchanging energy with all other grid points. So you can see each grid point as being in a sort of a canonical equilibrium, and then the whole system reflects that as well. So we've also investigated this in some other contexts, and even for fairly rough discretisations, a constant energy or microcanonical simulation agrees with canonical predictions already.
So what you're saying is you're essentially in the thermodynamic limit.
That's the limit I was trying to okay. Yes.
I was supposing the fact that I don't know much about statistical mechanics, but I mean, obviously working in terms of probability measures.
Yeah.
I'm wondering if I'm used to calculus probability measuring optimal transport, by the idea of the distance between two measures is one of the key things. Does that also play a role here, or do they just lift that from statistical mechanics, or is it some?
Well, the distance between measure, so the relative entropy is often used as a distance between measures in a sense. So
It's not the same as anything like Vasastar distance. It's something different sort of distance.
sorry, it's
Well, in optimal transport, you use the Vasastar distance, which is essentially the transport cost from one measure to another. It's defined as a distance between probability measures, so it's completely different.
yeah.
Or if statistical mechanics. I wonder if this came from statistical mechanics originally.
Yeah. Well, it could come if it's similar. It could. What I don't know what the so we have the.
It might get a different name in a different context, but it probably came from somewhere.
So this is given a prior distribution pi and a second measure p, then the distance, the relative entropy is usually defined as the minus of the relative entropy as the distance, as a distance measure between these measures. Yeah.
Relative useful. Well, I mean, obviously used for different purposes. Imagine people have done that. It's just I'm not used to sort of how it's done.
Okay, thank you.
Thank you.